in the community. He's publishing his work at the very, very best conferences. He spent a couple of years in San Diego and is now in Michigan, which is one of the strongest research places in the U.S. when it comes to architecture. So, Jason.
Thank you. Is this Oh, okay, there it is. All right. Good. So I'm happy to be here after the journey across the ocean. And today I'm going to be talking about improving efficiency in warehouse scale computers, and really with a focus on what we can do to make multi-core architectures more efficient for the kinds of computation that we see emerging in this space. So as many of us know, computing has been changing. We're now moving from desktop machines to mobile platforms, highly portable laptops, tablets, and smartphones. And also, we have a lot of computing cycles in warehouse-scale computers, these data centers. So as Forrester Research recently noticed, the cloud was a $40 billion market in 2011 and will grow to a $241 billion market by 2020. So this is a very important space to consider when we're building systems and architectures for emerging applications. And so this picture shows two of Google's data centers. This is from 2007, so it's a bit old. Each one of these data centers is a football field in size. Now, data centers are tens of football fields in size. And in each of these buildings, we have tens of thousands of servers and hundreds of thousands of cores in a single building. So in these platforms, this is where we house the large-scale internet applications that we all know and love, like mail, Gmail, web search, social networking, Facebook, these kinds of applications. And it's expensive, costing hundreds of millions of dollars to billions of dollars to construct and operate these data centers. And my claim is that they're still inefficient, as they're still in their infancy in terms of the software system architecture and the hardware platforms we have in this domain. And so I'll get into a little bit more as to why I claim that we're still inefficient. But first, let's look at the grand challenge in today's warehouse-scale computers. So our community, industry, as well as academia, has been working on energy, power, reliability, fault tolerance, hardware costs, performance, and utilization. The work that I've been looking at focuses on performance and utilization. And as Urs Hasel and Luis Barroso recently note in Data Center as a Computer, very popular text that anyone interested in working in this space should have a look at, performance and server utilization matter just as much as hardware costs. Really what we're trying to do is we're minimizing the cost for serving each query. So if we can serve each query with less computation time, less energy resources, that means there's a higher margin for companies like Google, Facebook, and so forth. So we all know what performance is. That's how well things run with the computing resources we have. But utilization is another very important metric in this computing space. And so to illustrate this, how important this optimization objective is, a simple graph shows what utilization looks like in data centers. So this curve is from one of those data centers, from 2007, one of Google's data centers. And it shows the utilization we're at between 0 and 100, and the fraction of time that we're at that utilization. So notice the hump of the curve, most of the time we're around 30 to 40% utilization. This has moved a little bit to the right, but not enough. We're still trying to optimize it. And as we move this hump to the right, we're getting higher utilization for a larger fraction at a time. And this means we're spending less per query if we see that utilization as improving increasing the number of queries. And to put both of these metrics in perspective, a 1% improvement in either performance and utilization at the scale of Google's warehouse scale computers can result in millions of dollars saved. So every percent counts when you're improving these metrics fleet-wide. But when thinking about improving the efficiency of warehouse scale computers, it's important to reflect on the design of warehouse scale computers to date. The design philosophy of warehouse scale computers has been a functionality first, efficiency second philosophy, where web service companies try to deliver the service to the users and build an infrastructure that can do that, and then tune this infrastructure to be more and more efficient, right? And as a result, in designing the platforms to deliver these services, web service companies has used commodity components, multi-core x86 processors, open source software like Linux, GCC, the JVM, etc. And they stitch these components together for functionality and then tweak the stack and these components to improve efficiency over time. The problem with this kind of approach is these components were not originally designed for with warehouse scale computers in mind. And when you start with these general purpose components that were essentially envisioned serving the desktop space, you may miss unique aspects of the workloads that you're running or the system that you can exploit for higher efficiency in warehouse scale computers, right? And this is kind of what we see in the design of these systems. So one of the key design philosophies has been to take a view, and this is precisely how Google designs their hardware-software stack, is to view an entire warehouse scale computer as a single fabric of hundreds of thousands of nodes, right, of cores. And so when the job manager, which is a very important aspect of the stack, and later I'll describe how you can decompose the stack into 3 layers to look at in design, they have a single view as hundreds of thousands of cores. Applications request how many cores and how much memory they need, and a bin packing algorithm is used to place the services on the relevant machines that has those cores. But in fact, what we find in data centers is all cores are not created equal, and we have different generations of architectures in the system. And it's important to acknowledge this when we try to design the hardware-software stack. So on each of these machines, what we in fact have, although the scheduler sees each hardware context, right, each thread, as a logical CPU and schedules work without considering the complexity within the system, in a typical server, this is really what the system looks like. We have multiple sockets, we have NUMA, we have various levels of shared resources. This image shows a Dunnington Intel architecture where you have 3 levels of caches and 3 levels of sharing, essentially. So it matters a lot how you run things on a system like this, right? Simply delivering 4 compute units, 4 CPUs, is not going to give you the same performance in every case. And to illustrate that, we can look at the sharing with just 2 threads. If you place 2 threads on a single physical core, SMT, you're sharing core level resources, the L1, L2, bandwidth to memory, etc. As you move this thread across the set of cores, that set of logical CPUs that the scheduler acknowledges, the sharing patterns change. Now we're sharing the L2, bandwidth to memory. You move it once more, we're just sharing the L3 and bandwidth to memory. And if you place them on different sockets, you'll have to share the interconnect, and that becomes a point of contention. So we have an interesting complexity within a single box, and we need the software stack to acknowledge this complexity of the underlying multicore and the interaction of the application characteristics that define the kinds of resources that is shared or is dependent on in terms of maximizing your performance and minimizing the variability in performance. And we'll talk more about why this variability in performance is an important thing to optimize for. So it's important to understand key characteristics that steer design. And I argue we have to rethink the architecture. And so I spent some time working in this direction with some of my work, and I have some interesting findings to share when looking at the space. So one observation that kind of underlies the work I'll be talking today is that one key characteristic has been overlooked, and that's the diversity in execution environments. So let me define what an execution environment is. The execution environment of this task is the underlying microarchitecture that it's running on, multi-core architecture, coupled with the applications that are simultaneously running on this system, right? And so our job scheduler today, basically when an application arrives, right, that requires a certain amount of resources, it'll place this task across, shard it across a number of machines without acknowledging the underlying microarchitecture or what's running on this machine. This leads to a number of problems. Tasks aren't placed where they run, where they like to run, where they run best. Tasks can't adapt to changes in the environment. And we're not able to manage phenomena that occur within the environment, such as interference in those shared resources. And so the current design of the whole system stack kind of ignores this, these aspects of the execution environment that would be important in maximizing performance, minimizing utilization. So let's take a look at, well, what does this variability look like? So we take the same three architectures. We have a Clovertown Generation 1 Xeon, an Opteron Istanbul, this is K10, and we have a Westmere kind of Nehalem server-grade architecture. These are actually systems that you would find in a single cluster in Google's data center, right? And all cores across these systems are treated as equal. So what are the implications of that? Here we have 9 Google jobs running across each of the 3 types of architecture shown as Clovertown, Istanbul, Westmere. And this shows the normalized performance improvement over the poorest performing architecture, right? And so we see that in some cases it matters a lot where you run in the data center. You get beyond 3x performance for Bigtable. In other cases, like Protobuf, it matters very little where you run. For search scoring, we see a preference that goes against the trend, right? We also see a preference that goes against the trend for map. This is face detection for maps, right, that runs in the data center. And so we see that architectural heterogeneity causes a varying amount of performance variability across, and it's very application specific. So execution environments matter in terms of application performance when it comes to microarchitecture. Well, what about co-runners? In a similar experiment, we co-run each of our tasks with various other applications across the same system. It's not important to understand what each and every bar means here, but the key thing to observe is the fact that the degradation from contention for shared resources on that multi-core varies across machines and across co-runners. So we have a lot of variability in who applications like to run with, right? And so we observe that in both of these aspects, it matters a lot where you run and who you run with. So we have a huge impact on performance, and we want to be able to exploit and adapt to where we run and who we run with, right? So there's been a lot of work across the stack that we've done in the lab, and it's important to acknowledge that designing the right solutions in this space requires looking across layers of the stack. And so we've done some work in computer architecture, runtime systems, compilers, and workload characterizations. Today I'll talk about some observations we've made in a few of these works, and I encourage everyone to have a look at some of the work that we've done. So there are 3 key design points for acknowledging this kind of diversity that we have inside of the execution environments within a single cluster. at the cluster level, we want to adapt how we place jobs to run across the fabric of cores that we find in the system. At the machine level, we want jobs to be able to adapt and react to the dynamism inside of a single node. And we want to be able to handle interference within the node at both the cluster and machine levels. We want to place jobs near who they like to run with and be able to mitigate the interference that we have on a single system when they're running together. So that's the kind of overview of the space that we're looking at. And I'm going to describe in more detail the problems of interference and how we can adapt and react to that. So when we're talking about interference, as I mentioned before, we're essentially talking about interference for resources that we're not capable of explicitly managing right now in the operating system. If the working set of your applications fit neatly in your private caches, you get great scalability in terms of the parallelism you can exploit. However, as soon as you rely on shared resources, you impact each other's performance between the two applications, right? So we can have these undesirable degradations. And this is particularly undesirable for applications that are user-facing, and that's what we find in warehouse-scale computers. Applications like web search, where if your query takes twice as long in some cases, that's just unacceptable, right, for the quality of service requirements. And to highlight this point, let's look at how contention leads to low utilization. So we have latency-sensitive, latency-critical applications like web search, and we also have I'll call that high priority, and we also have low-priority applications that are batch applications, such as encrypting your email, or with video, when you submit video to YouTube, encoding that into various formats. These are things that are batch applications that are not latency sensitive. You submit the video and you're done, it'll become live at some point, not latency critical. So there's two options when trying to eliminate contention. You can first disallow colocation, right? So you do not allow batch applications to co-run with your latency critical applications. And this is wasteful because we're underutilized, the systems are underutilized. That's the first option, right? We have peak performance on the system because we're not interfered with. The second option is to allow interference and potentially have degradation that is not acceptable, right? And just tolerate that variability. So user A might have a great time surfing the web via Google, and user B might have to wait very long for his queries to come back. Google chooses not to take this option, as do many other web service providers. And so essentially we disallow colocation, and this has been the approach, and it's starting to change now based on some of the work that we've done. However, the problem with this option A is that utilization is low. With low utilization, cost per query goes up. And what can we do about this? So one of the problems in this space is that there's uncertainty. Not everything necessarily contends with each other, because some applications can have great local cache locality, right? Private cache locality. And so there's this uncertainty of whether an application will interfere with your latency critical job. And this uncertainty, being unable to measure that dynamically and being unable to quantify exactly how much interference an arbitrary job may cause to the application, just leads to the approach of, well, we'll take the lower utilization, disallow colocation. So uncertainty is really one of the culprits in that low utilization. If we knew who was safe to run with our application, we can allow safe colocations. Let me highlight this point. So this graph shows the performance of Search Renderer. This is a very important user-facing workload that consumes a lot of the cycles we find at Google. this is the performance of Search Renderer when co-located with a range of other binaries, essentially, that consume a lot of cycles at Google. And what we find with a latency, with a quality of service requirement of, say, 90% of the performance when it runs alone on the machine, adds Bigtable and Semantic Analyzer violate that quality of service requirement, while the other three applications, Maps, Protobuf, and Sawzall, does not violate that quality of service interference. So we know that some of these applications are safe to co-run, while others aren't. However, prior to some work I'm going to talk about, it was very difficult to precisely predict the performance that you would have with the various co-locations. And so that's what leads to this low utilization. We say, well, we don't know who's going to hurt our latency sensitive application, so let's be safe and deliver the service to the users at the level that would satisfy them. So the question arises as to, well, what can we do to eliminate this uncertainty? Can we identify the workloads that are safe to co-locate? And this is one of the questions I undertook while spending some time at Google. So what we aim to do is allow arbitrary co-locations. Given arbitrary co-locations, allow the ones that are safe. And this needs to be a general methodology that's platform agnostic, because remember, we have multiple different types of machines within a single cluster, and deployable at the scale of modern warehouse scale computers, right? The challenge is there's a significant amount of prior work in contention. So we know how to predict who is more or less contentious. However, short of actually trying the co-location out for all possible, pairings of applications, it was very difficult to pinpoint, well, how many percentage points of performance will I lose with a prior, with an arbitrary co-location? And this is hard because we're trying to capture the interaction between resources that are not explicitly manageable in current hardware. This may change, let's see, but in current hardware, you can't explicitly manage your last level cache or your bandwidth to memory. And while the quadratic profiling methodology is straightforward, just try it all and see who hurts whom the most at peak load. But it's not suitable at the scale of warehouse scale computers, where you have many, many different potential binaries, and it would consume a lot of resources. It'd be very expensive to try the cross product of all applications. So is a linear solution possible? Is there a profiling approach where you can profile your binary once, all of your binaries once, and then you can identify arbitrary collocations, how they interfere with each other? Well, one of the key insights that drove how we tried to address this problem is to acknowledge that a white box approach, when you're dealing with commodity hardware, where you don't have the design specs and there's a lot of trade secrets in there, may not be the most suitable. So here's why, and I just alluded to it. There's high complexity in that you have to model all of the various points of contention, and some of these points might be secret sauce, like the design of the prefetcher or the design of the replacement policy and so forth is secret sauce to companies that sell you their commodity chips like Intel and AMD. It's not portable. You'd have to do this for every architecture you wanted to model, and it may not be feasible for that secret sauce. So the question we asked in this work is a black box approach possible? Lower in complexity because it's just one black box you can take from system to system, portable, and deployable on real hardware, right? So you don't need to understand the secret sauce. And to identify this approach, I use an analogy. The design philosophy we took is to imagine that you're a man in the dark room or a woman in the dark room, and you're trying to feel out the layout of the room. That's your memory system, right? And can you sense what's going on in your memory system, even though you can't explicitly see everything by touch? And it'll make sense why this analogy really, relates. So that led us to this idea of bubble up. But one thing I want to point out here is I think that this is an important design philosophy when you're dealing with systems that have you want to extract information from that system, but you don't explicitly have knowledge as to, well, how is it designed, which is the case with a lot of proprietary systems out there. And so we came up with this idea of bubble up. What we were doing is we're capturing the sensitivity of all of our applications and also the aggressiveness in the memory system so that we can compose the representation of this sensitivity and the aggressiveness to produce a precise prediction of exactly how much performance points we lose. So given these two applications, search renderer and some arbitrary co-runner, can we take our representation of the sensitivity and the co-runner's aggressiveness, and when run on a multi-core system, can we compose these two to produce a precise prediction? And this illustration shows the types of representations we use with the bubble up system. This representation of sensitivity is what we call a sensitivity curve, and the representation of the co-runner is the aggressiveness score. So with the aggressiveness score, we can look up in this curve what the prediction would be. And you'll see in the next slide exactly how this works. And so the design of the methodology that gives us the sensitivity curve, we use something we call a bubble, right? And the bubble is a stress test designed in software that generates pressure on the memory system in a dialable way. So as you turn up that pressure dial, the amount of pressure the bubble generates on the memory system increases, and as it increases, it records how the application is being affected by increasing amounts of pressure in the memory system, right? And there you get a curve. So as the pressure goes up, your quality of service goes down, and you have a curve for each quality of service. The second step in the methodology is to get the aggressiveness score. So as the application runs, we have a tuned reporter that will output how much pressure it feels the application that's co-running with it is generating, and that correlates to the bubble size that it predicts, and that's how we get our aggressiveness score. So I won't get into too many details of why it works. It's important just to know that there is a set of design principles that must be followed to minimize the error, right? Because this is an approximation, of course. If you capture the high-order resources, the hypothesis is your error will be small, and good bubble design is key. And we outline in detail in the work exactly how you design a good bubble. And so I'd point you guys to that to get more details. But let's see how well this methodology works, where we use this kind of black box pressure dial. So in this experimental scenario, and remember this is a scenario, so it's a controlled environment. We take 500 machines running web search renderer. And these are real machines, real production machines, running search renderer. And each instance of search renderer, and it's important to understand this setup, each instance of search renderer is configured to use 3 cores on a 6-core socket. And the 3 cores are free for a co-runner. So basically, the system is at 50% utilization. We have 500 jobs ready to run, and an even mixture of the 17 other Google applications we have. And we let co-location decisions be driven by bubble up. So here's our baseline. We're at 50% utilization, because every system is running search renderer, and half the cores are free. When we allow bubble up to specify the co-locations that are safe within that will only generate 1% performance interference, that's what this bar shows. So we go from 50% to close to 70% by allowing the co-locations we identify are safe. And these would be the applications that have great locality in the L1 or various other, they could be streaming and not being cached in a very contentious way. There's a number of ways you can be not very contentious. And as we reduce the quality of service policy, that is, how much interference would we allow? So 95 means we cannot affect the performance of our latency-sensitive application by more than 5%, we increase the quality of service significantly, the utilization significantly. So what we have is significant improvements at 99%, and at 90%, we have almost more than 80% improvement. And so we have a utilization improvement of 50% over our baseline at the 98% quality of service policy. So this is a big number. And we can expect some fraction of this number to work in production. This past summer, I actually spent some more time at Google and put systems like this in production. And the results are very good. I debated whether I should throw them on the slides, but I haven't gotten official clearance yet. But you may see something soon. But what about violations, right? It's an approximation, so we might actually violate the quality of service in some cases. Well, we reduce violations significantly at every requirement. And here's a key point. When we do violate the quality of service requirement, we violate it by very small number of percentage points. So here we show the yellow shows violating it by less than 1%, and really, on average, we violate it by, the worst error is 2.2%, between 2 and 3. So in these small cases, we have 2%. That is, we predicted 98, and we came in at 96. That would be a 2% error, right? So it's actually very close. It's not way off. It's also portable across platforms, because we have a similarly small amount of violations. Utilization wins. And remember, it's not how high these bars are, because this is a prediction. The various systems, this was the K10 Opteron and the Clover 2 Xeon, these have smaller caches, so you're going to have more contention. Our goal is to predict the contention, right? And we actually do a very good job predicting it here. However, and more details in the paper, you can check it. However, there's a couple limitations. I mean, this is a profiling methodology, right? So it's static. You have to have a priori knowledge of all the applications. So there are 3 limitations to this approach: an ability to adapt. So with A, B, and C on this curve, this is time. This is the load that the data center is getting. We have different sensitivity curves at different amounts of load. So we have an inability to adapt. That's the first limitation. The second limitation is we require a priori knowledge of the programs that you're going to run. And so that's illustrated by D with the question mark. And then the third limitation is the scalability of the number of things you can collocate. Being able to run 2 latency-sensitive applications on a single node at Google is actually a big win, as they actually require 4 cores here, 6 cores there, etc. However, it'd be nice if we can run an arbitrary number of predict precisely an arbitrary number of applications. And so we have a new work that solves each of those 3 objectives. And I'd point you to that work to find out more details, because I want to cover some of these other areas that we can improve system design for warehouse-scale computers. So machine level. What can we do at the machine level to have jobs adapt to their environment? And so this is another approach that has to work for large-scale environments with real systems and be very negligible performance impact. So the problem here is, given our compiler generating a web search binary, this binary can run in multiple environments, right? Various systems loaded at various levels. However, the binary we generate is rigid, right? It doesn't change as the environment changes. And this leads to some inflexibility. One problem that arises from this is the problem of aggressive compiler optimization. These are optimizations that sometimes will give you an improvement, other times will give you a degradation in performance. So sometimes your application goes faster, other times it goes slower. And then sometimes we don't know how it'll perform because it depends on other environmental aspects, such as who it's co-running with and so forth. So we need a mechanism for cracking this rigidness. What can we do to make our binaries more adaptive? This is kind of a hard problem. Traditional approaches use dynamic binary translators, but these are huge in complexity and you sacrifice a significant amount of performance. To achieve a deployable solution within warehouse-scale computers, you must be lightweight, low complexity, or people just won't pick up the approach. So we need a new technology for online adaptation, or really a new paradigm to enable online adaptation. And so that was one of the major challenges with this work. Prior approaches, let's look at the problems with binary adaptation, binary translation. So when you use dynamic binary translation or modification, your application runs atop a runtime that has to maintain fine-grained control of your instruction stream and your basic blocks at the basic block level. And so what happens is this runtime will interpret the application instructions, place regions of code in a code cache for efficiency, and only code in that code cache can run on the underlying processor. Otherwise, you lose control of the binary and things break. Right? It's one of the key rules of dynamic translation or binary optimization. You also have expensive transitions from the code cache to the runtime to manage things like indirect branches. And to do any interesting things with dynamic instrumentation, you typically require dynamic optimization, you typically require instrumentation, and then this instrumentation often needs to jump back to a runtime to do interesting things. So there's a lot of complexity here, and it also leads to a lot of overhead out of the box. So a new philosophy for binary translation that I embrace is to allow the binary to run natively on the system and have a very thin runtime layer, and allow the compiler to stitch in reconfigurability into the binary, right? So essentially, you anticipate the various dynamic situations that you want to specialize your code for, and dynamically you detect when you're in that situation and reroute your binary through the code regions that are relevant to the dynamic situation. And so we call this system loaf. And the nice thing about this system is you can control the overhead by how much you interfere with the binary based on the profiling technique. So built this out in GCC. Basically, it uses multi-versioning, and we have a global table that will specify the routing through the binary that's relevant. And we allow this dynamic introspection engine to change that routing based on information it can collect from the performance counters. And so this philosophy is very effective in that performance counting is very cheap on modern hardware. And so we leverage this. We use an approach we call periodic probing that can periodically collect performance counting information to detect the system configuration and reroute the binary accordingly. So what about that problem that I discussed before, the aggressive optimizations that may improve or degrade performance? How can we leverage this system to attack that problem? So this diagram shows the process we go through. There's a learning phase dynamically and an action phase. As our application executes, the runtime layer will read counters during the learning phase at fixed time periods and analyze the performance implications of various selections of routings through the binary, through the aggressive code. And during the action phase, it'll select the winning approach. We call this a competition heuristics because we allow various optimizations to compete based on who's performing better. And we do this continuously throughout execution. This approach works quite well. So the results we collected here was on spec. And what we find is when you use this kind of adaptation, and this is a CGO work from 2009, when we use this kind of adaptation, instead of, so here we have the application benchmarks, and here we have execution time on the y-axis. The first 4 configurations are static configurations, where we statically compile the binary with either cache prefetching, loop unrolling, or both cache prefetching and loop unrolling. And what we observe is that across the applications, you have various impact on execution time. Sometimes we win when it's lower than 100%, and other times we lose when it's higher than 100%. And what we observe is when we allow our approach, LOAF, we call this OAAO, Online Aiding and Abetting of Aggressive Optimization. It's way too long of an acronym. But when we use that, we always beat O2, right? And we significantly, and we don't suffer, the degradations associated with aggressive optimization. So over a baseline of O2, we have a 4 to 10% performance improvement across the applications. So this approach was relatively successful. And after working on this prototype at Google for a summer, Sriram Tallman picked up the prototype. It was very broken and did a lot of heavy lifting to get it checked into GCC 4.8. So this is actually a version of the approach is present in GCC 4.8, which is really cool. And Google actually uses it as binaries move from architecture to architecture in production. And there's some key insights behind this approach. It's actually relatively straightforward, and multi-versioning has been used for things like constant propagation before, but it's important to acknowledge some of the insights as to what this means for the way we approach executing our applications moving forward. I believe it's important to embrace vertical integration across the stack, right? We want to have our software systems talking to our underlying architecture to know what the best things are to do. We want to also involve the compiler to stitch in more reconfigurability. I think there's a lot of opportunity to enable dynamic responsiveness by statically stitching in, the reconfigurability. Performance monitor is key to online software techniques moving forward, and really we should explore more what kinds of counters we need to do better things in software. Right now there's still, and it surprises me that there's still not that much discussion between a lot of the system software folks and the architecture folks in really providing a plethora of counters for specific software needs in as general a way as possible. And I believe the day will come when all code and systems will continually be restructuring like the warming of a cache. And so that's at the node level how we can adapt applications to their execution environment in a way that's deployable on current hardware, that can scale, and that does not generate a lot of overhead. So now let's look at the, how much time do I have left? 10? Beautiful. So now let's look at the cluster level. What can we do at the cluster level to improve the system software stack to allow it to acknowledge execution environments, diversity? So really this aspect, the first thing you'd want to do is place jobs where they like to run, right? Just use that information to perform the scheduling. Let's ask the question as to what is the opportunity there. So you've seen this picture, homogeneous assumption, right? And we've seen that in these isolated experiments, there's a lot of variability in performance. So let's optimize this, right? So the goal here is to incorporate the awareness of this EE diversity into the software stack and map jobs according to where they like to run. We want to leverage the unique properties of the warehouse scale computer when designing an approach that makes sense in a production environment. Here we have a set of applications that are running continually in the data center. These are the services that you use. And we also have continuous profiling mechanisms fleet-wide. And this is really, really key. We have tons and tons of performance information that's logged and databased, entered into databases over the entire lifetime of the data center, and this is production information. Can we leverage this already abundant, already present information to drive some of the adaptive approaches that we want to achieve in the data center? For instance, here's one profiling system that's currently available, deployed at wide scale. It functions as a distributed service. Google-wide profiling, GWP, functions as a distributed service. It samples all of the binaries running in the fleet at periodic intervals, right? It's a sampling methodology. It collects things like IPC, branch mispredictions, all the good stuff you can easily grab from performance counters today. It's extremely lightweight. And this is why it can run all the time, about 0.1% overhead and always on. And it's currently being used by humans for debugging and performance analysis. Basically, they're like, oh, well, what happened in that data center when things ran really slow? And they'll go and they'll actually fix it. Google employs, thousands of SREs, software reliability engineers. And their entire job is to analyze performance anomalies and fix things as they go wrong. My question is, can you build systems that can do some of this stuff automatically? We have a plethora of data. It's essentially a big data problem. This is actually the tip of the iceberg when it comes to these kinds of software tools. And the key insight here is we want to leverage these software tools for automated systems, and it's a big data problem. So what kind of system can we build to place jobs where they like to run? So in this work, we have Wheremap, a WSC heterogeneous Where mapper. And essentially, we extend the job mapper to include this system that takes information from GWP, organizes it in such a way that you can run an optimization function that will instruct the job mapper as to where jobs like to run, and actually give a prediction as to how much better will it run, based on historical information from hundreds of thousands of nodes fleet-wide. And so we build a knowledge bank. The way Wheremap works is we build a knowledge bank of types and the relevant performance information, and we continuously train a scorer with this GWP information, this historical runtime information. And GWP continues to continuously sample all of this information and collects and aggregates this performance counter information. So to achieve the placing of jobs where they like to run, we formulate mapping as an optimization problem, and we construct a model based on information collected into our knowledge bank. This knowledge is each job's placement, so it collects information about its execution environment. What microarchitecture? Who was it running with? At the time, what was its performance profile? And thousands and thousands of instances of this data. So we aggregate this, and we formulate as an optimization problem and use a stochastic hill climbing algorithm to identify predicted optimal mappings based on the performance information in the knowledge bank. How we build a knowledge bank, there's a lot of data about this and information about this in the work, but I'll just briefly summarize some of how we build a knowledge bank. As time passes, it's important to note that the quality of the knowledge bank improves as we get more and more data of jobs running across the fleet. And I'll point you to two important aspects that for this talk. There's actually a lot more insights in the work, but observe Wherem and Wheremcs. This is policies as to how much data we want to collect. If you wanted to collect all of the possible co-pairings, that'll take a lot longer than if you're just looking for what architectures does it like. So essentially, Wherem is which architectures do I like to run, and MCS is which architectures and co-runners do I like to run on. So how well does this work? Similar setup. We have 500 machines, 3 production machine configuration types. We have 1,000 jobs, 9 composed of a random mixture of 9 Google applications. And it's from the PerfLab benchmark suite. This is a benchmark suite of all of Google's actual commercial binaries running on a log of hundreds of thousands of queries. So basically, these binaries are fed hundreds of thousands of queries and churns on them. And that's the PerfLab suite. It's not public. And we also did an experimental test bed with Spec 2006. It turns out there's a significant opportunity when you try to place jobs where they like to run. So in our Google testbed, and this is the normalized IPS, instructions per second, cluster-wide, across the 500 machines. The improved IPS is about a 15% improvement. One is normalized, all this data is normalized to every job running on the best machine that it likes alone, right? So one's essentially unachievable, but it provides a nice comparison point to see how far off are we from every job running in the best situation. And the blue bar, oblivious, is the performance we have with the status quo, arbitrarily placing jobs where they like to run. And Wherem and MCS shows about 15% improvement. The key thing to note here is that Wherem and MCF are not that far off for Google applications. And this is because there's a significant amount of Google applications that don't interfere with each other. What we saw was about a 20% to 30% degradation in performance from contention, and we saw a 3x to 3.5x performance variability in the machine type. So that's why we get most of the value from just focusing on machine type. It changes for spec, right? Because spec has you could see from the green bar, just looking at contention, gives us a little bit more value. So the workload actually matters. But overall, what we see is a 15% improvement in performance when trying to place job where they like to run. There's also one more really interesting insight from this work. If we just look at Istanbul, and this is 500 machines, all Istanbul, this is a K10 AMD machine, what we find is when you have 250 Clovertown, this cluster of bars is 250 Clovertown and 250 Istanbul, we match the performance, right? When we take advantage of the heterogeneity. This is because some jobs prefer to run on Clovertown and others prefer to run on Istanbul. The key thing to note here is this is much cheaper, right? You have the older generation Clovertown, which is significantly less pricey than the Istanbul, right? And so you can build a cheaper data center and match the performance when you take advantage of heterogeneity. We did a production analysis in the fleet, in the wild, and we see that across 10 anonymized data centers, we have a similar amounts of performance opportunity from 15% in some cases, to 5% in others. And to wrap up, it's important to acknowledge the emergent heterogeneity across machines in warehouse scale computers. The key here is you want to take advantage of continuous monitoring services like GWP, and not only for debugging for humans, but can we build systems that can automatically aggregate and exploit that information to improve systems. And there's a lot more in the paper, opportunity factor, that really impacts how you design such a system. So the key takeaways from this bulk of work is we need to do a lot to bridge the hardware-software gap. We need to allow our system software stack to exploit application characteristics to better run on our microarchitectures. And we also have to change the way we think about optimization. From a performance-only paradigm to quality of service, we have to acknowledge unique properties of of applications running in this space. Assume that you'll have co-running applications and how that affects the optimization decisions you make. Server utilization is an important metric. And as we all know, power and energy is also important to optimize for. And so with that, I'll take questions.
Yeah, Zora?